will not assume that you remember what's in lecture 1, so I'll just recall. I'll just recall that. So I'm taking G locally compact, second countable group. And again, you can think either think G discrete or G is SLNR with the nice topology that comes from Rn or R. Okay, so definition, proposition, the following are equivalent. The trivial representation is isolated in G hat, and any representation IH with almost invariant vectors has an invariant vector. And sometimes we write that as T weakly contained in pi implies T contained in pi. So weakly contained means that pi can approximate what T does, and then if you can approximate what T does, you actually can do what T does. And then there's like a more quantitative version, which is that there exists S epsilon, and S is contained in G finite, and epsilon is greater than 0, such that either pi has an invariant vector or the max of elements S and S that move psi out of itself is greater than epsilon times the norm of psi for any psi in H. I guess psi non-zero. All right, and there is another equivalent definition.
Do you mean S compact in general?
Oh, S compact, yeah. Sorry. And there's another equivalent definition which I didn't really discuss, but I'm just going to mention it. It's equivalent to and if one of those equivalent conditions holds, then you say that G is probably T. And any finite dimensional, all finite dimensional representation are isolated in GI. So basically, I'm trying to have a mental representation. So this is G twiddle. And I'm just defining. I'm writing it as a cube because I like cubes. It's not a cube, right? But anyway, here's G twiddle, and then there's this. So this is G twiddle, and then there's this G hat, which is the irreducible one. They're contained in all unitary representation, and here here you have the trivial one, and it's isolated when you're in G hat, but in G twiddle you can get close. But when you get close, you actually hit it. And the other finite dimensional representation are doing the same, and in fact, that you can read from this book that I'm leaving here. It's the same as all finite dimensional representations are isolated, or there exists one dimension, finite dimension. So, right. So finite dimensional representations are isolated, so they're not going to help you. They're not going to help you for property T. It's just so the trivial representation is a marker for property T. It's not on this representation that you can say anything about property T. Right. Okay. So then a remark, because now that we have a property, we need to, the next thing you want to do if you're a geometric group theorist is you have your favorite groups and you're like, does it have property T or not? That's what you do when you're a group theorist. Each time you hear a property for a group, you want to know if your favorite group or favorite class of group, maybe you don't have a favorite class of group, the group you know are fancy or well known. You want to know if they're property T. And so for property T, the answer is a little bit frustrating. And I'll tell you more about that. But first a comment, which is that if G has T, and I should have like a better spacing of what I'm doing. If G has T and H is closed subgroup and normal, then G mod H has T as well. And so, well, so that's not that difficult to see, because well, it requires, so here's a very non-enlightening proof, which is that this map here is continuous. So the induced map on G hat is continuous as well. So it's going to preserve isolated points. So if the trivial representation is isolated in G, it's going to be isolated in G mod H as well. You can also do it like more in a way that you see a little bit more, but you might need. Do you need induced representation? Yeah, no. You have so you have a representation here. You get a representation here by precomposing, and then you have to see that if you have an almost invariant vector here, the precomposition also gives you an almost invariant vector. You get an invariant vector. It's just going to be just as invariant when you mod out. So, yeah. All right. And then an important proposition, which I'm going to do, is that if G is amenable, then L2G, then the regular representation has almost invariant vectors. So right. So before I do that, let me just. So the regular representation is lambda going through G. So now I'm just going to do the discrete case. The continuous case is similar. You just have to be a little bit more careful about the measure you have in your group. But so lambda G is so now I'm on little L2, and yeah, just a comment about Hilbert spaces. So there's only one. And I always found that a little bit confusing, because if there is only one, why do you bother? That looks like there's one for each G. And in fact, so that's not true. There's a bunch of finite dimensional Hilbert spaces. So, we mark Hilbert spaces. So there's Cn. So it's a vector space with an inner product that takes value in C. So you have C to the power n. Those are the finite dimensional ones. And then there is L2n, which is the infinite dimensional one. And then with countable bases. And if you're infinite dimensional with countable bases, you're isometrically isomorphic to this guy. And if you have uncountable bases, I'm going to panic. So don't talk to me about that. Okay. And so right. So there's only one. So why do you bother writing L2 of G? Why don't you write L2 of n? Because so G is countable. Well, I say discrete, but I mean countable, really. So if G in the countable case, when you write L2 of G, you can just count and just write L2 of n. But you want to write L2 of G because if you write L2 of G, you're going to remember this regular representation. In fact, when you write L2 of G, you don't mean L2 of G. You mean L2 of n with a bunch of unitary operators, with a way of moving around stuff. Right. So okay, and right. So that was my Hilbert space comments, and so this proposition say if you're amenable, then you have almost invariant vector, and the other comment is that L2G has invariant vectors, which is a comment I already did yesterday, if and only if G is finite. Because, because the representation I have of L2G, an element in L2G, is something like this. And then G is going to move your thing around, and so if the only way you can be invariant is to be constant, but constant and infinite set that charges every point, where you have to count every point. That means you're zero. Okay, so now you're going to collect this proposition with this remark. So with this proposition, so proposition implies that Z doesn't have T. Because Z is amenable. I haven't recalled you what amenable is, but I'll do it right now. So Z doesn't have property T, so each time you have a Z quotient, you can't have property T. So that already, if you want to know, does my favorite group has property T? If you have infinite quotient, infinite abelianization, that's it. If you subject them to an abelian group, you're done. You don't have property T. And so that's why there's some open right. So I guess I can mention some open questions. The famous open question is do mapping class group have T and no. But the reason why we'd like to know is because people are interested in first homology groups, and if you have property T, first homology group is going to be finite. And so that's for free, that gives you that all those first homology groups are not there. All right, and maybe I should mention, well, I'll mention later more groups that do or do not have property T. I think Marek Kaluga is here. Are you here? No, it didn't show up for that. But anyway, he showed property T for, I think, out of n, but yeah, for some out of n. And the proof is some kind of somehow disappointing for many people because you need a computer if you're slightly computer phobic. That's a problem. Oh, anyway, so let me just go to the proof of this proposition. So let me say recall, and if you don't know, it's a definition. G is amenable if and only if. And I'm going to give the, so amenability has 1,000 definitions, and I'm going to give the one that I need. Actually, it's the one they prefer. Maybe there's another. If and only if for any f contained in G finite and epsilon greater than 0, there exists U that depends on this finite set and epsilon. Such that if you take the symmetric difference between, so this is Fu. So when I do that, you think G is equal to Z, and F is equal to, let's say, plus or minus 1. And epsilon is small. So there is this. So do you take a finite epsilon? So you find a set such that, so Fu is the set moved by U. So that's my set U, and I move it by U, and I take and I thicken it by U, and I take the symmetric difference. So I'm going to have something like this, Fu, and the symmetric difference is this thing here. And you want it to be small compared to the size of U. So if you're in Z, you're going to take U is some interval 0, n for n large enough. And then when you move it by F, you're going to get that Fu, the symmetric difference is 2. And then you take n large enough so that 2 divided by n, so that 2 divided by n is less than epsilon. Great. So once you've done that, you take psi, which is the characteristic function of U divided by the square root. This is the normalized characteristic function of U. And then you compute. You can see that pi s psi minus psi. If you look at the norm, so you have pi s. That's good. Psi is this bump is going to move it around a little bit. But when you remove psi, this is exactly the this is going to be 1. If I guess I should just you know what? I guess I'm going to do it like this. I'm going to take psi u, and then when I do that, I'm going to get something that's bounded by the symmetric difference between u and u. No, I guess I should have left it. Okay, sorry. And this is, you have this 1 over u that comes out, and this is less than epsilon. Okay, so your vector is small, right? Okay. And as a corollary, G with the abelianization is finite or compact. Okay. Right. And so amenable groups, well, they include all abelian groups.
If G has property T, then...
Sorry?
You mean if G has property T, then...
Yeah. Yeah. Yeah, right. If G has T, okay. So amenability is another very interesting subject, which I find it's a bit deceiving, because in fact it looks that you can do stuff, but in fact when you actually try to do stuff, it's harder than expected. But right, all abelian groups are amenable, and it's the same. You know, abelian group is just Zn, more or less, and the same proof works for Zn. You can see it in the same way, and right. Okay, so that's a way of telling that a bunch of groups don't have property T. Because if you know that all the quotients are finite, it's not enough to deduce property T. If you know that all abelianization, it's not enough. Okay, so question? Okay, so let me just go to the result I told you I would prove, which is the theorem by Margulis that says that. Okay, I guess I'm just going to give you a spoiler before. SL and R and SL and Z have T for n greater or equal to 3. So that's the spoiler for the rest of the talk, so that you don't suspect me to bother you with something that's just finite groups. I'm not discussing just finite groups right now. So the theorem by Margulis, which is really interesting once you know that SL and Z has property T, is that if G has T, then and G is finitely generated by S, H has finite index in G, then H of the Cayley graph of G mod H is greater than epsilon. Okay, and then so recall that H of a graph, So my graph is VE. That's going to be the min. So that's the boundary that Alan discussed, divided by the size of W, and the empty set is different in W, and W is contained in the set of vertices, and the size of W is less than or equal than a half times the size of V. So that's Cheeger constant or expansion constant. Right, that's the Cheeger or the expansion constant. And the Cayley graph. What's a Cayley graph? It's a graph. The vertices are the elements. So if you have a group which is finitely generated, the Cayley graph is a graph where you put vertices are the elements of the group, and you go from one to the other. If you can go from one to the other using an element in your finally generating set. So for instance, for Z, you have, if you generate it by plus or minus 1, like I did here, you have this line, but Cayley graphs can get really complicated. And if you have a group, if you have a subgroup, then the quotient is no longer called a Cayley graph unless your group is normal, but you still get a graph. Because you can still wonder, can I get from this coset to this other coset using one single generator? And if yes, then you put an edge. If no, you don't. Okay, so proof. So my Hilbert space is going to be L2 of G mod H. And I'm going to assume that the cardinality of G mod H is n. I mean, I'm going to denote that by n. And and I'm going to, there's an inner product on L2 of G mod H that I'm going to choose. You can change your inner products on a finite Hilbert space. And well, you have some so you can define this as to be 1 over n sum x in G mod H f of x g of x bar. So that's an inner product, and you have lambda of the semi-regular representation gf. Oh, right, bad notation. Psi, eta, psi, eta. Psi. That's the problem with using several references. All right, so this guy is in L2 of G mod H. So really, it's a finite vector. Yeah, because L2 of G mod H is finite, so it's just a function from a coset you assign the number, a complex number. And so this is going to be psi of G inverse X. And now what you do, now you're going to decompose H as the constant functions, direct sum with the orthogonal complement. So this is the constant functions. So this is also the invariant vector. And now I can erase. You'll remember the definition. No, maybe I'm just going to erase it. So by the way, I asked Pierre-Emmanuel if I was going too slow. And he said, no, you can chill, you can go slower. So that's me chilling. Okay, right, so you decompose your thing. And so it means that when you look at, so it means that you can cut your representation, and you have the representation which goes from G to U of H0. Let me put the 0 in. So this thing has no invariant vectors. Now you're going to take W contained in G mod H, and you want W, which I'm going to denote by little w, to be less than or equal to half n, and then I'm going to look at the function, which is the characteristic function of W, but I'm going to project it on H0, which means I'm removing a constant function, which is W divided by N. That's in H0. So, so T implies that for some S in S, so I'm using this one. For some S in S, you have that epsilon squared times the norm of F squared is less than or equal to lambda SF minus F. But this is because of the definition, because we just subtracted a constant from here. So this is the same as the norm of lambda S characteristic function of W. And here I gave you, oh, there's squares. Here I gave you the definition of the norm, which is the inner product of F with itself. So if you spell it out, it's going to be equal to 1 over n sum x in G mod H, the absolute value of 1 over U S inverse H, because that's the action here, minus 1W of X. And now you start recognizing the boundary of W, because who's going to count? If you're really, so here is your W. If you're somewhere in the middle and then S doesn't do anything, just stays inside, that's going to be 1 minus 1. If you're far out and you move a little bit, this is going to be 0 minus 0. But if you're here, that's going to start counting. And so this is smaller. Well, all right. So this is smaller than the boundary of W divided by N, because you have your N here, and then now you compute the norm of F. You have to trust me on that. It's a simple computation, but you get W divided by N, 1 minus W divided by N. And this is greater or equal to 1/2, because this is less than a half, so 1 minus this guy is greater than a half. So now you plug it in here, and so this means that dEW divided by N is greater or equal to epsilon squared times a half W over N. And that's it, you're done. That's it, we're done. We have that, we have what we wanted. Okay, is that what I... Okay. All right. So that's how you get expanders from a property T group. Because then what you do, well, so you can either, if you want a non-infinite collection of expanders, then you have to know that SL and Z has enough finite index subgroups. So you find them with Z mod NZ. If you look at the map, for now. Oh, let's go here. Right, so now we're gonna wonder, okay, how do I find finite index subgroups in SL and Z? You reduce modulo M, and you see that you subject to SL and Z mod NZ, and the kernel is going to have a finite index. And that's how you find, actually SL and Z is residually finite, so we know that it has a bunch of finite quotients. Okay. Okay, so let me just tell you another consequence of property T, which is if G has property. Now I'm not in the finitely generated case anymore. I'm in the locally compact case. And if G has property T, then G is unimodular. And so what does it mean to be unimodular? So delta from G to I plus can be defined as delta G. It's mu G divided by mu G. So what does that mean? So mu G is a left Haar measure. So it means that it's a measure on G such that the measure, a measurable set A, is the same as the one you displace on the left. But it doesn't need to be invariant when you displace your set on the right. If in your head all you have is a discrete group, then this is kind of mysteriously useless. Because if in the case of a discrete group, the Haar measure is you're going to count how many elements you have in your set. And if you move it on the right or you move it on the left, it's okay, you still have the same number of sets. Moving by element of G is a bijection. So it's not going to change how many elements you have. But if you have and if your group is abelian, again, it doesn't change if you move it from the right. But if you're in a, but it could be that, I mean, it could be that you take a set and you move it, and it doesn't change when you move it from the left. But if you move it from the right, it's just go wacko. And so that's the, you can have the analogous. You can have the analog. Well, most of the time the groups I deal with are unimodular, because if you have, for instance, a discrete co-compact subgroup and it forces you to be unimodular, and SL and Z is unimodular. And anyway, so there is a result that says that this is well defined. It's not obvious from how I define it, but this is well defined because I define it using a measurable set, a finite measure. So it's not trivial that it's well defined, but it is. And the thing is that this thing is a continuous homomorphism to R plus multiplicative. And well, and if you have property T, then your image in here is going to be an amenable group that has property T. The only one is trivial. So, okay, there's a continuous homomorphism. So, image of delta contained in R plus is a compact group. So it's the trivial subgroup. And typically the right. Okay. So let me just talk about SL and R a little bit. And okay, there's a result that I'm not going to prove in full, but I'm going to mention. Which is the following theorem. If you have gamma contained in G, finite co-volume. So it doesn't mean it means it's a discrete closed subgroup that has a finite volume fundamental domain. Then G has T if and only if gamma has T. All right. So I think if you think that gamma and G are both discrete hence finitely generated groups. Finite covariance means finite index. And I guess I could kind of leave that as an exercise to show that you go back and forth with finite index. That's relatively, I mean, with what I'm going to tell you, it's maybe doable. What time is it? All right, I have 4 minutes. Is that it? 4 minutes. In 4 minutes, I guess. Yeah. So I'm not. And in the case you're locally compact group, then one direction. So in general, okay. So if G is discrete, try to do that as an exercise. And otherwise, I will do that. And the other direction, meaning that if the lattice has T, then the whole thing has probably T, is a bit more difficult. But it's done in Margulis' book. I don't think you do it in your book, right?
Sorry?
That if you have a lattice that has T, then it goes to the ambient space. I think I looked at. I think it's not in the old version. It's maybe probably in the new version, but and it's in Margulis' book. But anyway, I won't do it. And so how do you have to go? If you want to go from one group to an ambient group, you have to induce up representations, and that's what I'm doing now. So you take induced representations. So you take pi h representation of gamma, and you're going to define K, which is the set of psi from G to H, measurable, and you want psi of GH to be equal to pi H inverse. It's some form of equivariance for H in, oh, I should have said gamma. And you also want that the norm of T squared, which is the integral over G mod H of sine x squared d mu x is finite. So, right, so mu is G invariant probability measure on G mod H. So if G were to be discrete, G mod H, you would just count every point to have weight 1 over n, where n is the weight. So that's a Hilbert space. And the action, the induced action from gamma to G of the representation P on an element C on an element X is just going to be f of c of g inverse x. So basically, what's the induced representation? What's important to know about the induced representation? So that works for any that actually works for any group to a supergroup. The finite covolume is important if you want to have almost invariant vector going from one place to the other. But what's important to notice is that if you induce the trivial representation from if you have H, which is let's skip to gamma. If you induce the trivial representation, you get the semi-regular representation G mod gamma. And in fact, the trivial representation, the regular representation is the induced representation from the trivial subgroup. The trivial group, there was only one representation. So, and the picture I have in mind is I have G here, and then I have my cosets. And I have a representation, so I know what your representation is doing on each piece, and I'm going to patch it up. The only way I know how to do it, meaning using the regular representation. And right, so I guess I'm out of time, so I'm going to stop here. And next time I'm going to do, so next time SL3R as T, and maybe I'll talk a little bit more about induced representation. Thank you very much.
Are there any questions from the audience?
I missed what was happening at the end. What is the role of this capital K that you define?
That's a Hilbert space. That's a new Hilbert space on which you're going to act.
Okay.
That's the Hilbert space for this induced representation.
Yeah, and what is little g in that definition?
Oh, right. It's that's another representation. It has this long weird name, but it's really another representation. Yeah, so it needs a G and it needs a C.
Right.
Yes.
Okay.
Yeah.
In the proof of Magruder's theorem that you get expanders from groups of property T, we didn't quite use the full strength of property T, so we only considered very specific representations, in particular only finite dimensional ones. And I was wondering if you know whether there are groups that might not satisfy property T, but where you can still build expanders in that way.
Yeah, ton of them. In fact, well, so you can build a ton. Well, since you can get any group out of Fn, you can get expanders out of quotients of free groups. Then a few years ago, Martin Kasabov looked at symmetric groups of finite, the groups of permutation of finite, a symmetric group of rank n, and he managed to find a generating set that turns them into expanders. So by hand.
Yeah.
Or not by hand, actually, with all his intuition from property T, he found a generating set that makes the symmetric groups expanders. And then there is another property which is weaker, it's called property tau, and that's like the kind of the minimal version, the minimal thing to get a bunch of expanders easily, I think.
Okay.
Yeah.
All right, thank you.
Any other questions? No, then thanks Indira again. We meet again at 10.